Hey everybody, we're going to be making a video today about simple harmonic motion and how it connects to an energy graph. All right, so you can see in the problem statement here, we have a graph that shows the variation of kinetic energy with respect to displacement of a particle that has a given mass performing SHM, simple harmonic motion. Now remember with this, we talked about this in our class, that we have this idea of being able to put the position on the x-axis and then the kinetic energy, or the energy in general, on the y-axis. Now the reason why is because we have an object that's going back and forth, whether sideways or up and down or something like that, but it's going through the same positions over and over and over again, and as it's at each of those positions, it has a certain amount of energy. All right, so the first question that's being asked of us here is it's asking us for the total energy of the particle. All right, now the total energy of the particle is the sum of the kinetic and all of the potential energies. Now in the center here, you can see that the kinetic energy is at a maximum. Now in these problems, we generally say that when the kinetic energy is at a maximum, the potential energies add up to zero because there's no more potential to gain kinetic energy. And so if the potential energy is zero at that point, then that means that the amount of kinetic energy that we have at this point right here is equal to the maximum amount of energy that it can have. All right? And so therefore, what is the total energy of the particle? Well, I can see right on my graph that it is 80 millijoules. Now, if I wanted to draw that into the graph, I could. I could just draw a horizontal line right here, and that horizontal line would represent the total energy. All right? Now, the second question is, what is the maximum speed of the particle? Now, the maximum speed of the particle I can get from the kinetic energy, right? I know I'm looking for a connection between what I have, which is kinetic energy and position, and speed. And so as I'm thinking about those things, I think back to my equations and I look through my formula packet and I find that there is an equation that says kinetic energy, it's in your formula packet, it's EK equals so you see here in the formula sheet, right here, you've got EK equals 1/2 mv squared. All right, so that's what we're going to be using in order to solve this problem. So we're going to say EK, I'm going to do the work down here so that I don't run out of space later. So EK equals 1/2 mv squared. Now I know at this point I'm looking for the maximum speed. The maximum speed, of course, is when I have the maximum kinetic energy. So I'll put in that 80 millijoules for my maximum kinetic energy here. So that will be 80 times 10 to the negative third, because it's millijoules. That then should be equal to 1/2 times the mass, which is 0.40, and then times v squared. And so that I can put into my calculator, whether I have a nice fancy one or just a scientific one just like this. So I'll take 80 times 10 to the negative third, and then I will divide that by 1/2, and then I will divide it by 0.4, and I get 0.4. Now that 0.4 is equal to v squared, right? So 0.4 equals v squared, and so now I'm going to square root both sides, and when I square root the 0.4, I get that v is equal to 0.6324. Now I'll notice that this has two significant figures. I assumed that that was right at 80, so that's also two significant figures, and so I'm going to write my answer as maybe to make this easier for you to see at home, 0.63 meters per second, or 63 centimeters per second. All right, so there we've got the maximum speed, 0.63 meters per The next question is the amplitude of motion. And actually, this is one of the easier ones as well, because I can get the amplitude straight from the graph. So in the graph, I can see that my object starts here. I can start anywhere on the graph, but the equilibrium point where the displacement is 0 is here at the center, and it goes over to -4 centimeters, and then it goes over to -4 this way. So the amplitude of oscillation is going from 0 to 4 to 0 to -4, and so the amplitude is 4 centimeters. It goes 4 centimeters that way, and then 4 centimeters that way. Remember, the amplitude is from the center to the maximum or minimum, and it should be the same in both directions for simple harmonic motion. So therefore, the amplitude will be 4 centimeters. All right? The next question asks for the potential energy when the displacement is 2 centimeters. All right? Well, for this, remember that the total energy is the sum of the kinetic energy and the potential energies, right? And so if I remember that, total energy equals the potential energy, so EP, plus the kinetic energy, EK, that should give me the answer. Now, I know that the total energy at any point in time is 80 millijoules. And so I can go ahead and now put 80 millijoules right here. The potential energy, that's what I'm looking for. And so all I need is to know the kinetic energy at that point in time. And so it says when the displacement is 2 centimeters. So 2 centimeters would be right here. So I just follow that line up. And it looks like it's pretty close to 60 millijoules right there. And so I go 60 millijoules, and I subtract that 60 from both sides, and I get that the potential energy is equal to 20 millijoules. Just like that. Piece of cake, right? Now, again, that should kind of make sense, because when I look at the graph, this is the kinetic energy. So this much right here is kinetic energy. And then the leftover from here to here, that would be the potential energy. They have to add together to give me that total energy. And you can tell that that goes from 60 to 80, and that is 20 millijoules. All right, so there we go. We've got the potential energy, which would be 20 millijoules. All right, so we're almost done with this question. We got one more section left. The next section is, what is the period of motion? So this is going to be a little bit harder, but we can figure this out. So the question is, what is the period of motion? And so I'm going to look for an equation that has period in it. I say, well, I don't really see any equation. I've got the period, which is period equals 2 pi over omega. I've got period of 2 pi square root m over k, but that's for a spring, so not that one. I've got period equals 2 pi square root of L over G, but that's for a pendulum, so it can't be that one. So it looks like the only one really that I can go with then is that the period is equal to 2 pi over omega. So I'm going to go with that one. Okay, so we're going to take, I need a new marker. Here we go. So we're going to say the period equals 2 pi over omega. So now the next question is, how do I get omega? Well, as I'm trying to look at this, I'm saying, well, I can't really see. I see an omega up here. Acceleration equals negative omega squared x. But I don't know what the acceleration is, so I don't think I can do that. I do know what the amplitude of the motion is, so I can't do that. Unfortunately, this is going to go into HL, isn't it? So the last part of this question, the period of motion, for this question right here can actually only be done by HLs. Okay, so if you are SL, you can stop watching this video right now. You don't need it, all right? But if you are in HL, you will have the tools that you need to be able to answer this question. Okay, when I'm looking for period of motion, the first thing I want to do is I want to go look for an equation that has period in it, right? So I'm thinking about period, I'm looking around and I look at all the equations in my formula packet. I'm like, well, I only see a couple of equations that have period. One of them is period equals 2 pi over omega. So we use that one in class. So maybe we'll write that one down. I'm thinking that might be a good way to go, 2 pi over omega. But then we look at the others and we say, well, I've got the t equals 2 pi m over root k, but that's for spring. I've got t equals 2 pi square root of L over g, but that's for pendulum. And I don't see any others that even have period in them at all, right? And so at that point, I say, well, I must need to work with this one, but I need omega. So in order to get omega, what we're going to do is we're going to need one of our HL equations, all right? Now, if you look down at the bottom of the page at the additional higher level simple harmonic motion equations, you can see that there are two equations for energy down here, right? One of them is for the total energy, and the other one is for the potential energy. And so we're going to look at the total energy one because we're going to use that to find out what omega is, all right? So we're going to use this equation that is ET, the total energy, equals 1/2 m omega squared x naught squared, all right? We're going to put the numbers in there. We'll solve it that way, okay? So the total energy, we already know that. That's the 80 millijoules. So I'm going to go ahead and put in 80 times 10 to the negative third equals 1/2 times the mass, which is 0.4, times omega squared. That's what I'm trying to solve for here. So I'll leave the omega squared times x naught squared. So x naught is the amplitude. That's the maximum displacement. And so I already know what that is. That's 4 centimeters. So I'm going to put in 0.04 squared, just like that, okay? And so now I should be able to solve for omega. So I'm going to take that 80 e to the negative 3. I'm going to divide it by 0.5. I'm going to divide it by 0.4. And then I'm going to divide it by 0.04 squared. And I do all of that and I get 250. So 250 is equal to omega squared. All right? Now I just square root it. And I get 15.8. Again, I'm working, so I'm going to go ahead and write down the 15.8. 15.81, but 15.8 is fine. Okay? Now, I wrote down 3 digits, but I'm remembering that I only need 2 sig figs to answer the question, right? All of my stuff up here only had 2 sig figs. So in the end, I'm only going to have 2, but during my work, I go ahead and keep an extra digit. So I've got 15.8. So now I can put that into the question. And so now I'll go period equals 2 pi over 15.8. And so now I go 2 times pi divided by 15.81. And I get that the period is equal to 0.40 seconds. All right? 0.397, but I need 2 sig figs, so I do write it as 0.40, 0.40. All right? And that is the final answer for the period. So again, HLs, you want to be able to look at some of those extra equations, whether we've talked about them in class or not, they're on there. And so hopefully this will give you a little bit of help in being able to solve that question. SLs, if you're still with me, hopefully you're not, but if you are, you don't actually have to use that because you don't need this equation right here. Okay? There you go. That's our first question.